The primary bottleneck in modern orbital deployment is not reaching space, it is the logistics of the launch pad. Traditional multi-stage rockets rely on massive, complex infrastructure and require weeks of staging, fueling, and preparation before ignition. This extended timeline directly conflicts with the demands of the modern small satellite market. These operators require rapid, on-demand access to orbit to replace failing nodes or deploy new constellations, and they cannot afford to wait in a months-long queue. To bypass this bottleneck, Skyroot Aerospace developed the Vikram-I. It is India's new private orbital class launch vehicle, engineered specifically to eliminate pad infrastructure delays. The vehicle is named after Vikram Sarabhai, the pioneering physicist who founded the Indian space program, tying this modern private venture to the historical roots of India's aerospace engineering. The engineering team built the vehicle around one specific, unforgiving operational constraint. It must be capable of launching within 24 hours from virtually any location. Meeting a 24-hour launch window is not a matter of working faster. It requires a complete redesign of how a rocket is built, fueled, and fired. This diagram illustrates the baseline capability of the Vikram-I. It is designed to deploy up to 350 kilograms into low Earth orbit, or LEO. If we expand the view to a sun-synchronous orbit, a high-energy polar path that keeps the satellite in constant sunlight, the payload capacity drops to 260 kilograms because the rocket must expend more fuel to reach that specific trajectory. To carry these weights, the entire vehicle generates exactly 1,200 kilonewtons of total thrust. This creates a strict physics problem. Engineers must maximize the efficiency of that 1,200 kilonewtons to guarantee the customer's payload reaches orbit without wasting energy lifting the heavy structure of the rocket itself. In aerospace, the empty weight of the rocket is known as its dry mass. Every kilogram of dry mass is a kilogram stolen directly from the satellite payload capacity. To successfully lift 350 kilograms to orbit on a small lift thrust budget, the Vikram-I discards traditional heavy aerospace metals and relies entirely on advanced material science. Skyroot's solution to the dry mass problem is an all-carbon composite structure. From top to bottom, the vehicle's skin is spun from carbon fiber. Carbon composite offers exceptional structural rigidity while remaining a fraction of the weight of standard aerospace aluminum or titanium alloys. By drastically reducing the mass of the rocket's exterior shell, engineers directly increase the mass allowance for the customer satellites housed inside. Manufacturing entire rocket stages out of carbon composite is highly complex and expensive, but it allows the vehicle to carry enough payload to make the small satellite segment highly profitable. The carbon shell provides a lightweight skeleton with very few moving parts, prioritizing structural simplicity and operational reliability. A lightweight chassis is only half the equation. To actually meet the 24-hour launch mandate, the propulsion system driving that chassis requires a specific, highly stable chemistry. Traditional cryogenic liquid fuels, like super-chilled oxygen and hydrogen, immediately fail the 24-hour test. Cryogenic liquids boil off at room temperature. They require hours of complex thermal loading, heavy refrigeration infrastructure on the launch pad, and they cannot be stored inside the rocket long-term. This cross-section details the Vikram-I solution. The first 3 stages are completely solid-fueled. Solid propellant is stable and storable. Packed directly into the motor casing long before launch, it requires 0 pad fueling time. Once triggered, it ignites instantly. These 3 solid stages act as a sledgehammer, providing the immense, robust initial thrust required to punch through the thickest, most resistive parts of the Earth's atmosphere. Because the stages are pre-fueled, the vehicle can be transported fully loaded on a heavy truck, driven to an austere location, erected, and fired immediately. But solid fuel has a fatal flaw. Once you ignite a solid rocket motor, you cannot throttle it down, you cannot pause it, and you cannot restart it. It burns at maximum intensity until it is empty. That uncontrollable brute force guarantees the rocket leaves the ground on time, but it makes solid fuel completely useless for the delicate, precise maneuvers required to place a satellite into a specific orbital slot. To solve the control problem, Stage 4 of the Vikram-I utilizes a hypergolic liquid upper stage. This upper stage is driven by a cluster of 4 highly specialized Raman engines. To reduce the risk of mechanical failure, these engines are entirely 3D printed. This minimizes the total part count and eliminates heavy joints and welds. This schematic demonstrates a hypergolic engine. It uses two highly reactive chemicals that ignite instantly the moment they touch in the combustion chamber. Monomethyl hydrazine acts as the fuel, and nitrogen tetroxide acts as the oxidizer. Upon contact, they auto-ignite into expanding exhaust gas. Because the chemicals auto-ignite, the engine does not require heavy spark plugs or complex electrical ignition hardware. This strips away dead weight and improves the vehicle's dry mass efficiency. More importantly, because the ignition is chemical, the Stage 4 liquid engines can be rapidly pulsed, throttled, and restarted to make hyper-precise adjustments to the vehicle's trajectory. This creates a highly effective hybrid architecture. The three solid stages defeat gravity, and the hypergolic fourth stage sculpts the final orbit. Escaping the atmosphere means nothing if the payload is damaged during the final deployment sequence. Many traditional rockets use explosive pyrotechnic bolts to blast the satellite away from the fairing. This violent separation sends severe shockwaves through the delicate electronics of small satellites. Skyroot bypasses this risk by utilizing ultra-low shock pneumatic separation systems. Compressed gas gently and smoothly pushes the payloads into the vacuum. The entire final sequence is controlled by advanced avionics, which provide real-time guidance to coordinate the firing of the Raman engines and the release of the pneumatic separators. By combining restartable hypergolic engines with clean pneumatic deployment, the Vikram-I can maneuver through space, drop off a satellite, fly to a completely different altitude, and drop off another, placing multiple payloads into distinct orbits in a single mission. This logistical capability recently drew national attention, with the Prime Minister of India officially unveiling the first orbital rocket. The complete architecture relies on rigid adherence to weight and logistics, an all-carbon composite shell, 3 solid-fueled ascent stages, a 3D printed hypergolic upper stage, and pneumatic deployment. By stripping away cryogenic infrastructure and heavy alloys, Vikram-I compresses a process requiring months of staging into a 24-hour on-demand delivery service.